All right. What happened? There it goes. All right. So on Friday of last week, we started looking at significant figures and how to count or determine how many sig figs are in a given number. And then we're also going to be we also looked at how to count sig figs to determine how many sig figs you need in an answer of a calculated number. All right, so looking at this first one, we have a decimal point, and then we have one non-zero number and two zeros following that. How many sig figs should be in 0.600? All right, this one is actually 3. Remember, when it's after a decimal place, you start counting at the first non-zero number, and then anything after it is still counting. All right, so that one is 3. All right, how about the second one, 0.0509? 3. Start counting at the first non-zero number. All right, how many in 0.44003? 5. All right, in this one, everything counts. All right, so this one only has 2. And the last one is 3. All right. It may not make complete sense right now, but as you do this more, it should start making better sense. So one of the things is, so these would all just represent numbers that are given. If we were to use these in a calculation, then we would have to start using the rules for addition, subtraction, and all of that. I'm gonna play. So there's a couple of YouTube people that I like for that do videos for chemistry. One of them is this person, Melissa Maribel. You'll find I use a lot of her videos. Her videos are excellent for very specific topical things. Just about every concept that we do in this class, Melissa Maribel will have one. Sometimes she presents it a little bit differently than I do, but that's actually not a bad thing because you get to see that there's frequently more than one way to get to the right answer. And then we're not so different that she's doing that it looks like she's doing a whole different stuff. So I'm gonna go ahead and show this one. This kind of in 5 minutes shows what we did last Friday. So so just kind of pay attention to it and use it for reinforcement. All right, hold on. Let me turn up the volume. All right. So this one just asking how many sig figs. How many sig figs in question number one? One. Just the 7 counts. What about 2? 4. That one is 4. Everything counts. Number 3, 2. And number 4, 4. The 7.801. Remember the exponent in scientific notation, that part doesn't count to the numbers. All right. So again, she does a really good job, and there's a little bit more to this video, but I'm not gonna. I think she just kind of recaps everything, so I'm not going to show that. The thing is, there are a lot of different YouTubers out there. Tyler DeWitt, Miss Melissa Maribel are my favorites. I'll put their names up at some point. I think they do the best. Melissa Maribel hits it right at the level that we are teaching it. I think she's a former teacher that started making money off of this, so she went that way. Tyler DeWitt, I believe he's a college level professor because he tends to go a little bit beyond where we need to at times. So be careful with his videos because sometimes they can actually end up confusing you towards the end of them because he starts going a little further than we need to go. Not everything, but some of the time he'll do that. All right. And then there are several other ones. Some are better than others. Obviously, that's with any kind of product on that, but just kind of be careful of that. All right. So today we're going to kind of pick up where we left off. So we're going to begin looking at numbers in scientific notation. So like one of the numbers that she presented, that very last answer that she got, the 1,550, there's a better way to write it that's less ambiguous about the number of sig figs. We were looking for 3 sig figs on it. So she could have put that in scientific notation and it would have been a better way to show it. Doesn't mean you always have to show it that way. It's really kind of left up to you, but if you have something that's kind of ambiguous, we'll use scientific number notation. We're also going to go a little bit further with calculations, addition, subtraction, multiplication, division. In that, we're going to actually combine functions at the same time and see how the rules apply for both. All right, so that's where we're going today. It's not a lot of material, but it's just kind of looking at things as a whole. All right, so this number that's on the board represents a number that's in scientific notation. So we have, in any number that's scientific notation, you have 2 basic parts. You have what we call the decimal part. The decimal part is going to be any number. It's going to be a number that's between 1 and 10. actually really 1 and 9 because we try to keep scientific notation to the ones place. So notice this one is 1.2. That's our decimal part. All right. That's the part that applies to sig figs. All right. And then the other part is we have the multiplier. Or the exponential part. All right. An exponential part is 10 raised to an exponent. So we have that, in this case, we have 10 times negative 10. So when I look at this, the things that are really telling me information about this number, obviously the decimal part is the number that I'm dealing with. And then this part, I'm going to look at this exponent. If it is a negative exponent, what kind of number would you expect if we wrote this in standard form? It's a decimal. So if you see a negative exponent, that means it's going to be a small number, or a part of a whole. If you see a positive exponent, it's going to be a really large number. It gets bigger. All right, that's the kind of key thing to it. Sometimes the notes will say move the decimal to the right, move the decimal to the left, and I think it ends up confusing students because we stick to it one way all the time, and we forget that when we're going from standard to that, it's just the opposite. To scientific, it's just the opposite. And we forget to flip the direction. But I want you to think, if you have a decimal, you're going to have a negative exponent. If you have a whole number, it's going to be a positive exponent. If it's in scientific notation, you have a negative exponent, that means it's a small number. Positive exponent means it's a large number. All right, sorry. Did everybody have what they need off of this? All right. So a positive exponent means one multiplied by 10 times n times. A negative exponent is going to have a negative n on it. I don't even like how that was written. So let me all right. So converting a number to scientific notation. So let's say that we have the number 4,530. All right. If I'm doing this, the first thing I can look at is how many of those numbers are significant. 3. All right. So this is the part that we're looking at as far as our decimal part. Now, if I want to put this in decimal form, and I want to put it to a ones place, what do I need to do? All right, 4.530. So that's kind of so I need to move the decimal place to get between 1 and 10. So I don't have a decimal here, so I'm gonna, but it's assumed. So 1, 2, 3. So I have the number now 4.53 for my decimal part. Why am I not including the 0 in this? It's not significant. All right. So I have that. Now I also need to find the multiplier. So I need to figure out what I'm raising 10 to. I moved it 1, 2, 3 times. So I still need to keep the value of that 0, but I don't show the 0. All right. So it's going to be times 10 to the third. All right. So when I write this out, now, a lot of times you can use calculator to actually do it. So, if you punch in, um, 4,530 in here, and then do the function to go, so you would hit the second button and then the little science engineering button and switch it from flow to science. It's going to write, and you hit enter, it'll write it in scientific notation. The thing is it doesn't always get rid of the sig figs, sig fig stuff and all of that. So you still have to be aware of the rules and all. But this one tells us when I plug it into the calculator, this is what. Sometimes it'll give you something like this. 4.53 with a capital E to the third. That means the same thing. And in fact, whenever we're in a test for Southeastern and you have to enter in a response in scientific notation, this is the preferred method. All right. So, and I'm sure I'll get the question at the time, because it's going to be very hard for the test to auto grade the times 10 to the third. So I have to point it out to the professors whenever we do it that way and all. But that E to the third is going to be the format that we'll use. All right. And so that E3 means the same thing as times 10 to the third. All right. So let's look at a number, or actually go ahead, write down these numbers, and I want you to try them yourselves. And then we will. All right. So looking at this first one, 5983, how many sig figs are in this one? There's 4. So we're going to, when we move the decimal place, how many places are we going to move the decimal place? We're going to move it 3 places to get it to a ones place. So rewriting this number, I'm going to change it from 5,983 to 5.983. So there's 4 sig figs in it because everything counted. All right. But when I look at the number, notice that in this one, I'm not going to lose any numbers. All right. Now, what should my multiplier be? 10 to the third. All right. So notice how this was a large number. It gives you a positive exponent. All right. Next one, we have a decimal, 0.00034. How many sig figs? 2. So we're only going to be dealing with our 3 and our 4, and I need the decimal in between there. So in order to get the decimal there, how many places do I have to move the decimal? 4. So what is going to be my exponent this time? All right. So it'd be 3.4 times 10 to the negative 4. All right. Does that make sense? All right. So again, these zeros were leading zeros. They weren't significant. So the only numbers I was concerned with was the 3 and the 4 here, and I moved the decimal to get to the ones place. Same thing here. Everything was significant, but I moved the decimal between the 5 and the 9, and that was 3 places that I had to move it. This was 4 places, but because it was a decimal, it's a negative number, negative exponent. All right. So hopefully you know the rules for rounding, and this is just a review. But as we're going forward, we have to remember that when we're trying to write things using sig figs and using the proper format, we may have to round from time to time. So when numbers are used in the when numbers are used in a calculation, the result is rounded to reflect the significant figures of the data. So if we're doing multiplication division, one part of the given has 2 sig figs, the other one has 3. Our answer can only be in 2 sig figs. We may have to round to get to those 2. All right. The same rounding rules applies that you've always used. If the number immediately next to it is is 5 or above, we round it up. If it is less than 5, then we just drop the end. We don't round down, we just drop it. All right. Now, if we are doing problems that are multi-step, be careful and don't round in between steps. The thing that happens when we round in between steps is we do something called over-rounding, and it can make the number either much larger than it's supposed to be, or smaller, depending on if we're adding, subtracting, multiplying, dividing. So you want to maintain all of the numbers in there, just so that whenever you're doing your calculation, that we don't over-round it. And especially if you're going to take the number that you produce and plug it into another calculation later, if we over-round it, then we can end up with some significant differences. All right. So let's start looking. Let's start looking at a number. All right. So if I have the number 14,530,025. And I say to round this number to 2 sig figs. What's the numbers I need to look at in rounding this?
14.
Okay. I need to look at the 14, but I also need to look at what other number? The one right next to it. So I have to look at that 5 as well. So now when I write this number, how can I write this as 2 sig figs? Could write it as 15. million, or I could write it as
5 times 10 to the 6. Oh yeah, 7.
all right, so I can write it as 1.5 times 10 to the 7. All right, both of those end up being correct. So when we do this, when we're looking at rounding, remember we're going to look at the number that's immediately to the right of it, as we're pulling it in. All right. So what we just did, again, I'll write the number that we had, or close to it. Had a number something like that. So the book says use only the last or leftmost digit being dropped to decide in which direction to round. Ignore all the digits to the right. So we were trying to go to 2 sig figs, so I'm using that number. I don't care about those numbers. All right, I'm only using the 5, that 1 5. I'm not going to round the 5 at the very end to make that 2 or 3. Or if there was a sequence of number, I'm not going to round until I get to that point. I'm just going to round it one place on it. All right, and that gives us the 15 million. All right, remember round, and I hate using the word round. I hate using the expression round down. If the last digit is less than 4, we're just going to drop it. You don't round down. You don't decrease the number. You just maintain the value and you drop that number. All right. If the last digit, that we're looking at, the drop number is a 5 or more, we're going to round up. So I don't like how the book phrased that. All right. So we have the number 25,946. I want to put this to 2 sig figs.
2.6 times 10 to the 6.
All right, so we could say, we can put it in scientific notation. We could say 2.6. Why 2.6?
Because you have to round up.
All right, so because of this 9, I have to round the 5 to that. And I'm gonna also, we could also say 20,000, 26,000 there. All right, so it's going to be 2.6 times 10 to the 4th, or 26,000. All right. Questions, comments, concerns? All right. Now, what happens when we have a calculation that has mixed functions? So in this one, we have 3.489 times, open parentheses, 5.67 minus 2.3. Yes?
Do we use PEMDAS? So we do what's in the parentheses?
Yeah. So we're going to have to use order of operations, or, yeah, that one. So we have to do what's in the parentheses first. Now, some of these times, and I'm going to tell you on active and all of that, some of these are going to be kind of vague, especially if they're using a fraction thing. They'll do a fraction line where everything underneath the bottom of the fraction, it might be a subtraction problem underneath the bottom. and it's not going to show parentheses, but we have to assume that so we'd have to do what's one part before we can do the other. All right. So now I have to do that 5.67 times 2.3 first. So when I'm looking at addition subtraction rules, what's going to be the rule for my answer on this one? So I'm going to be careful not to say number of sig figs for addition subtraction. What can my answer only have as far as in the answer? One decimal place. So when I do this one, 5.67 minus 2.3, I get 3.37. But remember the statement I said, don't round in between steps. So what we have to recognize is now this number technically only has 2 sig figs in it because I'm about to multiply. So I'm saying 3.37, but actually I'm not going to round it yet, even though I know in my head it's kind of 3.4. All right. So moving on to the next step, we'll use the subtraction rule to determine what the intermediate answer is, and that the intermediate answer only has one decimal place. All right. So we end up with this number now, or this expression. Now, when you're doing this in real life, you're probably not going to write down every single step, and I get that. But I want you to be able to conceptually understand why this is going to have the answer that it's going to have. All right. So we have 3.489 times 3.37. I plug it into the calculator, and I get this. How many sig figs can my answer have? I can have 2 sig figs because after that subtraction problem, I end up with 2 sig figs to a 4 sig fig. So when I do this, I have to round. So my final answer is 12 because I can only have the 2. Yes?
So you still multiply by the full thing, but in your final answer,
Yeah. Yeah. So that's kind of why I put the line right here, is I'm just recognizing that that's where my actual sig fig place is. So in this one, I only have those as my 2 sig figs. And so here it's still just those 2 count, but I'm still, that 7's still there. The 7, yeah, it still has value. Now I want to be careful. Now on this one, if I'd have used the 30, if I'd have used 3.4, it probably wouldn't have thrown my calculation off very much. But I just want to be careful about doing those kind of things. All right. Any other questions on this before we move on? Does it make sense? That's the question I have. All right. A lot of times, this stuff is actually really easy as long as we don't overthink it. Some people tend to overthink it, and they end up doing more than they have to and over rounding and stuff like that. So just take it for what it is. This is just some rules about how we report our numbers and our answers on things. All right. Anybody need time? All right. So kind of to wrap up today, I'm going to give us 2 other little charts. Both of these should be things that you're familiar with. So in science, we try to use what's called the International System of Units, or SI. There are some base units that we use. So, and that should just say gram. So, base unit for length is the meter. Base unit for mass is the gram. Depending on the size of the object, sometimes we'll use kilogram as a base unit for it. But if we're dealing with small things, most of the stuff we're measuring in this class, we'll be using a gram. Time is seconds, and then temperature measures in a unit called Kelvin. Kelvin is essentially the same thing as Celsius, but Kelvin Kelvin is simply Celsius plus 273, 273.15 specifically. All right, but those are the 4 base units that I really want you to know. Just know that mass can either be gram or kilogram. In this class, most of the time we'll be using grams. I like to keep them all to a non-multiplied unit. The next slide that I show, I'm going to end up giving this to you, giving you a copy of this at some point. I just didn't have it made today. But I do want you to know the metric prefixes as to the base and all of that. So, just waiting for a couple of you to finish writing. And I'm actually probably going to, the next slide, I'm actually going to, before I give it to you as a handout, I'm going to rewrite it to include where base is on it. All right, does everybody have what they need off this slide? All right, so for the most part, you have probably spent time in that area between milli all the way to kilo, right? You've seen those. So those metric prefixes, we're not adding anything to it. And then also, I'm going to draw a line right here between this. Right in between deca and deci is where our base lies. That's the and I use these exponents more than I use the decimals and all of that. Base represents 10 to the 0. What does 10 to the 0 represent? 1. All right, 10 raised to the 0 power is 1. All right, so we kind of compare all of these back to that. So what? Whenever we say deca is 10 to the first, so it means it's 10 times bigger than a base unit. This is 100 times bigger than a base unit, 1,000 times bigger than a base unit, 1,000,000 times, and then whatever the word for 10 to the 9th is. All right. So as far as we're concerned in this class, I'll never go larger than giga. And for the most part, we only go down to micro and nano. So what I would write is I would write the giga and the capital G as that, and then I would write the exponential notation, because that's what I'm going to use whenever I talk about these numbers. All right. So giga all the way down to nano. Is what I'm going to be concerned. And remember, your base unit is going to be that meter, liter, gram, second, those kind of things. And then we can add those prefixes in front of it to change the value of the number.